Perfect. Just gonna set up my stuff. Code up that a Jacobi version of SVP. Okay, perfect, cool. So today, what I wanted to do was to actually try to solve a specific problem. I struggled last week with the singular value decomposition. It was the numerical version of it where you could just like that's it. You find every one of the eigenvalues and eigenvector, then you could directly construct your your two matrices and your one diagonal matrix. So today I wanted to go in another version of it, which is also kind of difficult to code, so I might struggle a bit, which is the Jacobi estimation. So it's not directly going at it to be 100% correct. We're gonna have to iterate on the solution until we hit like some bounding error that we're good at. So that's what we're gonna look at today. I'm gonna just do this one because last time it took me an hour and I think an hour 30 minutes just to get it right. So we're gonna be over there again, DeepML, unlock this stuff. There's two features that I discovered last week. There's this one where you can split like the bigger problem into smaller one, and then there's like this kind of notebook mode where you can like literally have a notebook. It's kind of a lead code platform, but like for like linear algebra, machine learning, or deep learning kind of a problem. So yeah, I'll go at it. Don't hesitate if you have like any questions, folks. It's like a study session for me, but also for you. So if you have any question about research, about deep learning, about machine learning, let me know, and I might be able to try to answer it. I'm starting to get a bit sick, so I'm gonna be a bit like slow-brained today. Hi, Sagne. Glad to have you here. Okay, so singular value decomposition. This we know. Basically, it's you have it's just to be able to turn a matrix, let's say a transformation matrix A, into three like sub matrices. There's the U here, there's a sigma, and then there's a V, and then like that these matrices have some inherent properties, right? This one is a diagonal one, so it's gonna look like this, right? And it's gonna be all zeros everywhere, so big fat zero here, big fat zero here, and then it's gonna be, from what I remember, I don't have that on top of my head, but sigma is a here we're just dealing with square matrices, right? So it's a square diagonal matrix containing the singular value of A. So this is why last time we were able to yeah, I'll do my best, Mo. Thank you for the wishes. That's why last time we were able to kind of find the singular value, right? And then like find the eigenvectors, and then just construct these matrices directly. It was a mess, but we got it through. But in this one, we won't be doing this. What we're going to be doing is you're going to have, you start only with A, right? And then iteratively, right, you're going to, at each, what we call sweep, through the stuff. Hi, Faima, how are you? Through each of the sweeps, right, what's going to happen is you're going to actually like construct this U, sigma, and V transpose matrix, right? But they're gonna suck, right? It's not gonna be working well, so it's gonna be like not good, right? And then like we're gonna have to. It's usually like this with these iterative type of algorithm, right? And you're gonna see them a bit everywhere, especially like in everything scientific computing, right? You're gonna see that. Even with machine learning, you're gonna see this a lot, like these type of algorithm where it's good enough. At some point, like you should stop because we're good. Usually, you see that with like something called an epsilon, right? Which will have like a very small number. Let's say like this, like 8 times or something like that, right? 0.1 like this, and then when between the true value or like the stopping criterion and this epsilon, the gap is small enough, right? You should stop and exit. So this, like if we get closer to this or error that is like that, this is good. If we're far from that, right? This is not good if we're far from that. That's usually how it goes. So yeah, so then you go and then you do multiple round at it. That's kind of what the Jacobi method is about. It's an iterative type of algorithm, and then you're going to be able to create the sigma, the u and the v, and that's it. And then this is what we return, I believe. Yeah, and right now in this thing we're saying it's a 2x2. So we have the baby version of this. So it should not be too difficult, right? We're gonna have like a 2x2 like this. We can even eyeball it. I think it's a 2x2 and symmetrical. Because here in this example A, we're gonna have a 2, 1, 1, 2. Well, yeah. So, not sure. I think one of the questions we might have is like, is this 2x2 symmetrical? I think that will help out, but anyway. So that's roughly what we're gonna go for, and yeah, the return stuff is this. So this is u. The first one is gonna be u. Then we're gonna have this array, which is gonna be sigma, right? And you see here, this is not a matrix; it's an array. So we're gonna have to return like this, but like the actual sigma thing is gonna be like a diagonal, right? So but this is just gonna be the diagonal element, I believe. So that's gonna be that. So these are the diagonal elements. And the last one will be the v, right? And in this case it's it seems to be all the same numbers everywhere. So, well, we'll see. Maybe they will not be different. I haven't done I haven't done this exercise, right? So I might get stuck for quite some time. Actually, we're gonna cheat a bit. We're gonna do run code just to check out the test result to see if like we're dealing with symmetrical matrices. And no, we're not. Like this one is not symmetrical, right? So I have my answer. So yeah, this is not symmetrical. So not answer. Oops. Not necessarily. Wow. Okay, cool, perfect. Okay, so we have everything except the actual algorithm. So let's learn a bit more about the Jacobi method. So singular value decomposition, can you see well right now? I think so. Okay, yeah, you're good. That's good enough. Yeah. SVD is a powerful matrix decomposition technique in linear algebra that expresses a matrix as the product of 3 other matrices. We already know that. So we have A, which is our original matrix. So this is a transform matrix. We have U, which is orthogonal, whose column are the left singular vector of A. And we have sigma, which is a square matrix, which is a diagonal one. And then VT, which is going to be an orthogonal matrix, column are the right singular vector. So the Jacobi method is an iterative algorithm used for diagonalizing a symmetric matrix through a series of rotation. Oh, well, what the hell? A symmetric matrix is a square matrix that remains unchanged when transposed, meaning its elements are mirrored across the main diagonal. Like, I don't have that. Like the second one is not as symmetric. Okay, I don't think this is that important because I know we can do it without. Yeah. Anyway. It is particularly suited for computing the singular value decomposition by iteratively applying rotation to minimize off-diagonal element until the matrix is diagonal. Okay, this is the high-level overview. I found like a nice, it's a nice video on YouTube. Actually, there's no sound. There's no. It's just music that is playing. It has a nice visual of like what is going on, right? So this is the roughly algorithm. You have this matrix. They say it's symmetrical. So maybe the second one won't work. I don't know. So here, right? We have an ellipsoid, intersect a coordinate plane in an ellipse, perform rotation in a coordinate plane to align the intersection ellipse with the axis. The corresponding AE ij becomes 0. Repeat until off-diagonal elements are all 0. So the off-diagonal elements are these, right? Like they're off the diagonal, and then we're just trying to rotate this until it's 0. So we're gonna see it in action, and it's pretty cool because you're gonna see with the matrix the manipulation we're doing. So if we are going here, here. So that's sorry. So this is the main matrix that we're dealing with, right? And then there's these here it's T. In another thing I've seen it written as a G, but like these are the Jacobian the Jacobi rotation matrix that we're gonna multiply the A with, and then like you will see these change. So we're trying to zero them out, right? But by zeroing them out, there's others that are gonna change. You see, like the diagonal is changing, but like also there's a side effect on all the other ones, right? Until like all the other ones are small enough that they don't really matter. So there's a bunch of rotation until we're good, and once we have that, like the resulting this thing, right? Like this diagonal is what we need for. I think this is for the U. If I remember correctly. Okay, so we start with this A transpose times A to find U and set. Sorry, this is for V, and this one is for U. So these one will be the identity matrix. And then the goal is to diagonal this one and this to obtain the V in the process. So we're gonna accumulate the stuff on the V and the U, right? So identify off-diagonal element in this to be minimized or zeroed out through rotation. Here it doesn't matter because we're just gonna alternate between like the two. In this case, it's I'm not sure. Like, are we just gonna do it on like this one and then this one and then iterate on that? This one is a 2, this one's a 3. I'm not sure how it's gonna play out. So okay, we start with that. We have the initialization, obtaining V in the process. Then we choose a rotation target. So we find one of them. It doesn't matter. And then we calculate the rotation angle. So for each target off diagonal element, calculate the angle theta. For the Jacobi rotation matrix J, that will zero it. That's involved solving for theta using blah, blah, to accurately handle the quadrant. So we have our off diagonal element, and then we have our diagonal element on the row and on the column. And in our case, it's gonna be like the two. We only have two numbers, right? We have this one and this one on the diagonal. So this is good. Okay. And then we apply the rotation, construct J using theta. This one I'm not sure how to do. Constructing the J and apply the rotation. I think I saw it in here. How to do it. Yeah, not sure. I'll double check that. Okay. Effectively reducing the magnitude of the target of diagonal element. So I do that, and then I guess I subtract. I think this is the stuff that we've seen here, where we're just multiplying these together. So I find that this matrix, I multiply it this way, and then like I'm gonna get the stuff. Okay. And I update V or U by multiplying it by J. Okay. So then repeat the process of selecting off diagonal element. We iterate, calculate rotation angle, and applying rotation until this is sufficiently diagonalized. So I think we're gonna have to have some epsilon in there to say like stop. Once diagonalized, the diagonal entry of this represents the squared singular value of A. And we're saying that sigma contains the singular value of A. So we just need to square root them. The matrix U and V are constructed from the accumulated rotation containing the left and right singular value vector of A respectively. Good. And then Jacobian method is practically effective for dense matrix. Okay. Okay. Cool. Okay. So let's actually go back over here and try to get some clarity. This is the same form as we've just seen in there, right? Over here. Wait, I'm just gonna replay that. So, right now it's moving, it's minimizing 1, 2 here. And then go 2, 3. Okay. So there's something called a given rotation matrix. So given the rotation change both of the rows addressed by it, the understanding. Okay. As with row addition, algorithm often choose this angle so that one specific element becomes 0, and whatever happens in the remaining column is considering acceptable side effect. In our case, it's more than acceptable side effect because, like, by doing this rotation, we get this diagonal, which is going to be our sigma. Okay. Okay, wait. By applying given rotation as a conjugate action, both rotating by one angle between two rows and rotating by the same angle between the corresponding column. In this case, the effect of the four elements affected by the rotation is more complicated. To the end of the derivative, okay. Okay, cool. Yes, okay. So, okay, let's go back here. So this is familiar. This stuff is what we're talking about over there. Roughly. That's roughly that. Yes, it's gonna give us right, okay. 2 times this, we're equal to all that. And if we want to isolate this, we go arctan, then we divide by 2, but we arctan this whole thing, right? Yeah, okay, cool. I think I'm starting to see a pattern here. Okay, so this is the angle. Okay, this is our angle here. It's given by that. Okay, so what we did is we took this, right, and then we did arctan on it, right, and then we have a 2 here. Yeah, but here, okay, yeah. This one we did divide by 2. Right here, and then we did the same thing over there. So by doing that, we have our 0.5. We have, why do I have a 2 here? I'm not sure why. Because this, is this 2? I'm really not sure. There's a 2 over there. Okay, so okay, this is that. And then what do we do? So oh, I think I get it. We're not trying to run this on A, we're trying to run this on A transpose times A, right? So this is what we're trying to do. So we're gonna do this on A transpose times A, and then like this whole thing at some point will give us our this would be the U one, right? This will be U, right? And then the other one, so A times A transpose, this one after like all of the stuff, it will give us our V because this start off as the identity matrix, right? I think so. So this start off like this, right? And then like we are doing the changes. So I think we're getting there. Okay, and this one is gonna be, I think it's gonna be symmetrical. So then we're good. Okay, I think I get it. Okay, so that's that. We have our U and V that will be changing. They start as the identity, and then so like these ones are kind of their separate process here. Like the U, well, okay, I think here like there's gonna be change on AT over here, right? Like this, right? There's gonna be change that's gonna happen over there, and at the end we're gonna get our diagonal, which like if you square them you're gonna get your sigma, right? That's that. Like that's what we're gonna get at the end. If we just follow this thread, we're just gonna get the sigma, but we're not gonna get the u's, and we're not gonna be able to recover them, because all the while this is happening, we need to go and then update with the data, right? I think it's by, is it like what it says? We have to accumulate, multiply this by j, right? Okay, cool. So we get that, we get our we get our angle. Somehow we get the angle here, right? And that will be related to this for sure. So we get our angle like that, and then like with the angle we get our j, and with the j, this is what we multiply by this, and we repeat that step however time that we need to repeat that, right? And doing this motion here, because at first it's not really you, it's like you can think a bit of it more of it's the identity, right? As we go through it, then at the end we get the u like that. And if we want to do it properly, the u and the v are connected, but like a brute force way here would be to just to do it parallel, like the same stuff, exact same stuff is happening here in parallel, just so that we can get our this doesn't matter, like it doesn't matter if we get that or not, but what matters is the process of getting the from I here to our V here. And it's going to be the same process here, same exact process with our J that is doing this. I think the angle, I'm not sure if the angle will be different. I think it's going to be different. I think it depends on the because like let's say this first test, let's look at it. Like I said, I absolutely haven't done this before, right? So like we're discovering all of this together, folks. I'm a new viewer. What are you using to learn? Website that guides you? Yeah, for sure. It's this website. I found it like I think it was 6 months ago when it was launched on Hacker News, and I clicked on it, and like it was exactly what I was looking for. I like to do lead code type of question to keep myself sharp, like with Pythons and like just like doing like programmatic puzzle. I love that, but I felt like there was never that for deep learning or machine learning in general, or like even the machine learning topic that you need. It's either you find a good book and then you follow through, right? There's a bunch that you can get, but then you find a good book and you go through it, or you're doing project, right? But like I might be in the minority here, but I kind of like lead code type of question. I find it's fun puzzles, right, to do. You get a puzzle, and then it's like gonna be kind of algorithmic. You need to know a certain type of stuff. Sometimes like you have like a context that you need to rip out and then find like I like these type of stuff, right? So I was looking for something like this for ML, and it's this guy actually, this dude that is leading the project, and he did it. So I'm just doing the puzzle from now on. Okay, cool. So we have that. Yeah, did I paste it yet? Yeah. Let's do some reverse engineering to understand what we don't understand over here. So in this first case, so this is my U. So this is my this one I don't care about. But like these two are exactly similar. Like this one, not exactly, no. They are opposite here. The diagonal is similar, but these two are flipped. Is it the same here? So I don't care about the sigma. They are not the same because this one is not it's not symmetrical from the get-go. So I think that you can I think that I've seen somebody that you can recover one from the other, but like in our case we're gonna go this way. We're gonna do like both of them in parallel. I will actually not do that. I think what I'm gonna do is gonna be a bit dumb. I'm gonna do this one first, right? And I'm gonna try to do this by just like attaching it together, and then I'm gonna use the method I'm doing over there to get my third one, which is gonna be my V, right? And I'm gonna do it. Jesus, can't write the 3. I'm gonna do it by just like using that function and just jamming the whole thing through. Okay. I think that's getting there. What else do we have? So this is to find the tan. This is to find the theta, and this one we know. This one we know. This one we know. Should be the off diagonal with the largest absolute value, called the pivot. Okay, I like this is interesting. Okay, here the off diagonal element to pick should be to be optimal the largest absolute value, called the pivot. Okay, cool. The Jacobi eigenvalue method repeatedly perform rotation. Okay. Then the approximation of the real eigenvalue of S. Okay. So if we have the pivot, and this is the largest absolute value, okay. Okay, this is the conversions to this. Okay. Okay, they have like a pseudocode for this. So this is for update. This is to find the element. Okay, I don't care too much about that. Okay, so how does it work? We do. This is the rotation. Well, no, this is the rotation, and then this is how it's working. And these are just function. That this look like some C pseudocode type of stuff. Okay. What is E in this case? It's T. Wait, what is it? Is a description of the Jacobian method in MATLAB. It calculates a vector E which contains the eigenvalue and a matrix E which contains the corresponding E vector for what? For S? By the way, folks, if you're writing something like pseudocode related in, I don't know, university for a paper, for the love of everything, right? Do not do this. Like, what is this? What the fuck is, what are we looking at, right? I, K, L, M, state, S, C. We have the whole alphabet in this. And then, like, this is a mathematician that does that. Like, they always do this shit. It's absolutely infuriating. Then you spend like what, like a solid solid like 2 hours trying to like to figure out what each of these means. I understand like it's like here, this is I goes here, then there's a K over there for like just the indexes. But come on, like every time I see something like this, it's absolutely infuriating. Anyway, so okay, we have that, and okay, wait. There's a cos and a sin involved over there, and then this is, I think this is it. I think this is the thing that I'm missing right now. Is this idea about the cos and the sins, where to place them. Because I get my theta and I can calculate all the causes, all the sins, and I bring them there into my matrix, and then I can just multiply my stuff by it. And I think that become my J, I guess. And I do this for N. Steps. But where's the repetition? Okay, here, wait. Here we're rotating this stuff. Why are we doing like this? Is it because we're rotating two things in this case? We're rotating the vector E and the matrix E, okay. There's the same pattern here, cos, sin, minus sin. Okay. And it's the same shit we're doing here also. This is for my S, this is for my E. And then update all, potentially change index. And we'll do that rotation n time. Okay. And I think this is by this, because this is where the cos sign minus sign is happening, given I and J in here. Okay, wait. C cos theta, S sin appear at the intersection I and J, rows and column. So for a fixed I bigger than J, the non-zero element of the givens matrix are given by everything else is 1. For K not equal to any of this. For K equal to IJ, J here, interchangeable between the two, we get the cos. And then everything else, IJ, so row, column, becomes minus sin, and this becomes sin. So we're doing the rotation by doing this times whatever of the vector. I think I get it. I think I'm starting to get it. Okay. Okay. I think we're guys, we're converging, right? We're doing a bit of a random walk sometime, but I think we're converging. So, and I understand now why is it 2 by 2, because if it was not 2 by 2, I would not be that. I think it would be fine. It would just be like a bit of a mess. So, in our case, we're dealing with off diagonal element, right? So we're never gonna try to change these ones. Like these ones we're not touching at all. Wait, yeah, we're not touching this at all. So these stay costs. They will have to stay costs, and then we're gonna alternate between the minus s and the s, depending on like depending on where we're at. Here is this says ij minus ij equal minus s. So this is like right now. This is the target because I is smaller than j in the wait, is that the this one? I think I'll have to get check. Okay, so if we select this, I think we're gonna see that pattern, right? And that's what we're gonna get. And then if we select the other one, we're gonna have to flip it and just give that here. I think that's how it's gonna work. So like it's alternate between these two that we're gonna change, and this one is gonna be row 1 0. We're gonna do that. Yeah, and this one's gonna be row 0 1, and that's the given matrix we call J here. And that's stuff. Wait, where's my video? And we're doing on this stuff, right? Because here it says symmetric matrix A, but in our case it's not that. It's gonna be our A transpose A times A multiply this one. Like this thing will be our symmetrical matrix. So what do we do here in order to do the we just need to multiply these two together. Find the angle, multiply them, get the result, and then we iterate. And like that stuff is our all right, I've read somewhere that like if this one is orthogonal to the other one, like it doesn't matter the the eigenvalue will be the same. So this is why we can do this manipulation. Okay, I think I get that. So we're building this, and in this thing, this is where we're gonna inject our theta, right? Our theta will be injected there, and we're gonna be able to get our costs in there. We're gonna be able to do that, get that in its specific format. And then what do? We take that soup, one of these two, and then we do what? We're gonna do what? We're gonna do like our A times AT. What's the stuff here? It's J transpose times this. Is it the same here? It's the opposite. I'm not sure it matters too much. And then you do you take that stuff and then you do J transpose dot that, right? You get these one first, equal, this is gonna be our pseudo sigma, right? Sigma prime. And then we do what? We find the theta again on this guy. So do we theta back on this one? I think so. Yeah, I think that's what we need to do, because here, let's say, like, it killed this one off, right? And then it selected this one, and it's modulating these, changing this shit a bit. And then, like, this one is small, you're going to the other one, but it's on the resulting matrix that you're doing. Okay, I think I get it. So this is the thing. If we bring it back over here, so after the iteration, let's say 1, we're gonna get our sigma prime, and we redo it again, and then we're gonna get here sigma prime prime until the element that we're selecting is very small. So sorry, I think here, what the heck, okay, here, this bit that I've discussed, every step, because we need to know when to stop this, right? We need to pick the largest element, and stop when it's smaller than an epsilon. Right. And then, like, you either go, or we're either gonna get one or the other, and that's that. And I think this is what we're trying to do. Was it here? No, it's the other one, right? Yeah, this one. This is what they're trying to do, max index here, right? They will tell you which I and j you need to get based on, like, a scanning of the off diagonal element. That's what they're doing. Are they stopping at some point or no? In this case, I don't think they have an epsilon. Maybe this. No, it's not that. No, I don't think they do. They just iterate. Yeah, they just iterate. Wait, what is it? You see this? Like, how can you read that stuff, right? How can you? There's not even any spaces in between, like, the lines. Like, you have, I don't know, man. I hate that. There are people, like, I once, like, had to debug air code base in air, R, sorry. I have nothing against R, absolutely not. But, like, it was written like this. There was no documentation whatsoever. There was no comment that much. Like, you have all of this soup of letters, and, like, why the person did that is, like, they were not necessarily like a very skills in terms of year of experience. So they took a bit of everything that they had, the snippets, and they put the whole code together. But it made no sense. Like, it was very difficult to understand. So the first thing I did was I went there and I refactored all the variables. That's all I did, and I saw a whole bunch of logical problem, because one variable was saying it was doing this thing, like this letter, but it was not anymore. It was another letter. Yeah. So yeah, you say it indexed at 1, but, like, I would have rather worked on R than the other alternative at my lab, which was MATLAB. I absolutely hate this language. Like, MATLAB is, I have no love for it. I worked on it for like 5 years for neuroscience research, and I absolutely hated every minute of it. There was not a single day when I was doing MATLAB code that I was like, yeah, this is fun, right? At some point, I got so fed up that I was writing most of my analysis in Python, and I was using like a binding in MATLAB to just like call Python. So when I was working with R, I was like, at least I can take a break from MATLAB stuff, even though it was a big pile of garbage. Yeah. Anyway, so moral of the story: if you're writing code like this, you're gonna confuse yourself, right? It doesn't matter. This is very general. I get it, right? Okay, it's fine. It's very general. You can put maybe more documentation than this and stuff. But if it's for like your practical use, and then like the stuff means something, let's say it means participant, it means like, I don't know, like EG data, whatever. Name it the stuff that it need to be named. It doesn't matter if the stuff is long. Like we have big screens. We're good, right? It doesn't matter. Like you don't have to have abbreviation and like letter soups for everything. It's fine if it's like very large, long text. The variable looks repetitive, right? Because you're reading and stuff and you can follow it easily. It's much better being boring like this than having people think about like what maybe you think, especially if the stuff might be wrong, right? In this case, I know that they're not wrong because like it's Wikipedia and like it's a fairly used algorithm, so for sure they double check that. But if I'm reading a code base, it's like that soup of letter, I would not trust anything that it's doing, especially if there's like some error somewhere in the pipeline. Okay, so Fahima asked, what are the parameters that we should change in a deep learning model to enhance accuracy? I also want to know what are the specific parts in the model that we can enhance in a CNN model, for example. That's a very good question, right? Let's take a small break from from this, right? So there's many things that you can change in a deep learning model, right? There's that's it. The first thing you can change, let's say you have an architecture, right, is the actual architecture. Actually, no, right? First thing you can change, I would say, is the data, right? Yeah, that's the first one, right? So, like, if you want to have better performance in your model, I would first and foremost not look anywhere near the model, right? Especially if the model, there you have something outputted, right? There's some accuracy that is outputted there, right? And then you're like, yeah, I'm getting like I don't know, like 82% ImageNet 1K with this model, right? First thing I will look at is like, is my data, can I make my data better, right? There's different ways of making your data better. One is just like having a heck load more of it, right? Two is to find if like, I don't know, there's ways of reducing the noise in your recordings in some sort. In our case, well, back in the days, we're doing EG, and like if the recording was not well done, there's a lot of noise. If there's a lot of noise, we need to clean a lot. If we need to clean a lot, we're going to remove a lot of data points, right? So like figuring out the data and figuring out how to get like either more, in this case, two parameters you have, like more or like better, right? If you can get both, more and better data, usually it just gonna lead to better model. Like that's kind of dumb, but that's kind of it, right? So you can have the same exact network, but you have more high quality data, it's fine. Even with like large language model, there was a bunch of research that showed that like reasoning, if you had very high quality reasoning traces and you were trying to do reinforcement learning on it, the model was just better than if you had like a whole bunch of them, reasoning traces, and you were trying to do reinforcement learning on like these like semi-stable reasoning prompt and answers. So like this is seen throughout everything, like even the image recognition and whatever it is, right? So like make sure that your data is of high quality. A lot of people and researchers usually just jump out of this. They just jump out, right? They just jump out of this whole thing and they start to mess around like the model and trying to make it fine tune this, fine tune that. The issue with this is you're gonna spend a lot of time waiting for the model to be done with your training, and then you do another pass and another pass. I always found that like it's fun, right? But it's not the work that need to be done. Like most of the work that need to be done is like almost janitor level type of work. You have to go into your data and like, yes, I will need to label a bunch more of them, or like I need to find ways of getting a heck load more of them, or like I need to clean it and spend more time like doing these manipulation, or I need to do data augmentation to model the noise that I'm gonna get in my in the real world setting. That type of stuff, right? First thing is this. Second thing that you can do, right, is read a bit more here, right? So read a bit more here. So what I mean by that, right? I mean by that is the like there's some, like if you take a base architecture from anywhere and then you just use that as your base, like usually models are improved in like just one way. Like you have a base that like the field, the size is good, and then you're gonna improve a bit this base by doing your like some change architecturally, or like some hyperparameter change that you're doing, right? So I highly suggest you to read more, right, about the different type of architecture that other peoples are using that kind of work with your stuff, right? So example, let's say you're doing something with like LLMs, right? And like you have long text, like we're talking super long text. We're talking like more than 128 tokens, like a million tokens and stuff, right? If you're not well read and you go with the usual type of GPT models and stuff like that, you might corner yourself into something that is not necessarily well fitted for this, because like most of these like use softmax, right, attention, which like as you have more tokens is just quadratic in terms of like the tokens length that you have. Well, if you read a bit more, you might find like I did actually a video on lightning attention. Yeah, this one. Like basically what they did in there is it's just this stuff, right? Basically what they did in there is that they figured a way to get linear time attention mechanism, right? But what it does effectively is that, where's this figure? Like it's much easier than to have a very long context length input, and for the kind of the same performance that you would get with a regular transformer, or a bit better for long context. So like this is to say that if you're not well read here and then you're going into your stuff with the specific architecture in mind, you might bottleneck yourself. Even if you tune the parameter, you're gonna bottleneck yourself into some sort of reality, right? That might not be exactly the best suited for your stuff. So read broadly, right? Like look at the different architecture for like your field, right? Look at like what other people maybe in another field is using to solve a similar problem, right? Once you have all of these architecture, like pick the most likely to be true. Keep the other in mind if like you're hitting a bottleneck, but like that's kind of how I would start with. Is you make sure here that you don't like box yourself somewhere that you shouldn't, right? Once you have that on check and you're like, yeah, like don't go crazy here and test like 100 different architecture, right? Like try to stay pragmatic. Then here you have to tweak like you can tweak like either roughly the architecture here, right? So like there's a bunch of hyperparameters. There's hyperparameters that pertain to wow, I can't write today. There's hyperparameter for the architecture, right? Jeez, here architecture. So the number of neurons, the numbers of layers, and whatever. Usually you're gonna be bounded by your resources, so your GPUs, right? Don't start too big at first. Like start small, and then try to build up this. Like if you're more confident, at the end you can go a bit bigger. And then there's like another type of hyperparameter that are just like the what's inside. So usually this is like the type of optimizer you're using. Are they using AdamW, or are they using like the very vanilla version of Adam, like some other like type of optimizer? And then like that's one version, and then like the parameters within these parameters, and then you can use like different type of methodology. Grid search is one. There's other kinds that are a bit more fancy, but this here you use like something like grid search, where you give like a whole array of parameters, and then with these parameters, like you on grid search, you're gonna be able to like kind of find the best setup for you, right? That's kind of that. You start with what's good for the field. Like that's that. Like this is sometimes a bit confusing, right? This and that. You start with what's working right now. You don't go with like the vanilla, like 0, 0, 0 everywhere, or like what you think is good, right? Or the default that comes packaged within your, like, don't do that. You go and read a paper, right? That match to most closely. You get the same architecture for you, and then you get the same exact parameters. And then in your paper, if you have to, you explain that you start from there, and then you do a grid search on like more parameters space, and then this is how yours differ from this like trunk, right? You differ in this specific manner. So yeah, that's kind of that. And like here, like the size is super important, right? Like it depends on what you're doing, but a size of a network absolutely crucial for some aspect. As the network gets bigger and bigger, there's some emerging capability within the network just by the sheer amount of size. That's pretty important to keep in mind. So yes, even if like you get some good result in some like lower network, always try like to go as far as you can go with your GPUs that you have available, just to see like, is there something funky happening with the larger size. Yeah, that's kind of that. One thing that I've seen over and over again is that what's inside, like usually simpler wins. I don't know why. Like usually the simpler blocks always wins. If you think about like value, still there. There's other variant and stuff, but it's still there. There's it should technically not work, but like it's still working, right? There's a whole bunch of these things that we like. Just this like you have your X here, it goes into whatever layers, and then you always see this in diagrams like that, right? Like this, let's say in the transformer architecture, you see it clearly. Let's say here, let's take this one, right? Are we gonna see anything? No, this is all pixelated. Okay, sorry, I'm gonna take a bigger one. This one. Yeah, perfect. So, like, you see this fine line over here that goes like this, right? You have another one that is like this, and like if you see everywhere, you have this nice line over there that it doesn't go into like the actual heads that are doing. So this dates back from like the ResNet days in like image recognition. It's a very simple idea, right? It's not even, that's it. It's really not complicated, but that idea, it sticks, right? And it just like works. It just works well. What it does is a bit complicated. Like it's reducing like the effective length of the network, so making stuff propagate more better. But this was in 2015, like this idea, 2015. This stuff is still there. Like this architectural changes are still in these models. Like ReLU, same thing. Like we're doing sigmoid, like kind of slow. You do ReLU, wow. Like now it's working well, and then like this stuff is still everywhere. Yeah. So like stay simple, but then like look at what the field is doing, and this is where maybe you can innovate a bit. Don't try to change everything every time, all like for your whole experiment, right? If you have a good trunk and then your data is good, and then like you're well read, so you know what's up. Usually this won't be like a shot in the dark. Like you already know you're gonna get some good baseline, and then just about improving it iteratively. Yeah, like that. Does it help, Faima? Yeah, true, James. Like usually the architecture is fixed, and you iterate through per parameter optimization plus improving the data. Yeah, that's 100% correct. Except if you're doing like architectural research, then like this is not fixed, and you might like go ahead and do some funky stuff. Okay, so where the heck was I? Where the heck was I? Okay, yeah, I figured this part out. I'll need to get that epsilon, that stuff, and I get my epsilon here. And I was ranting about this stuff. Yeah, true. Okay, so I get that part. This is how they're doing the update, which is how. I think the last thing that I need in there is like okay, get the rotation and then construct G and apply the rotation to this. So reducing the magnitude, okay, get that. And then I update that by multiplying by J. I think I have everything. I think I have everything at the moment. I don't have more. I don't need more. I'll work here on the notebook version of it, just so that like I can how do I make an array already? Jeez. I can see stuff. Create array. Yeah, okay, I'm just dumb. Okay, so let's say we have that. I have my nice array right now. And then I want to construct, so this is my matrix A. And then I want to construct my sigma. Let's call it like a temp equal A NP wait A I think it's just that T, right? That T, right? Then, no, it's not, yeah. Close A. Okay, so we're getting somewhere now. I'm just gonna take this whole side. Can we see stuff? Yeah, we can. Okay, so now I have my S step, right? And what I want to do, is to construct first my J, right? My J will be like that. Don't hesitate if you have other questions. By the way, I haven't forgot about that this member reproduction project that you wanted to do. I think with the visual member. I got like sidetracked a bit with like linear attention type of mechanism, but I'm gonna get back on it and like get it done. Okay, right. So now I have to like find the theta. And the theta, we already have the formula, which is this, right? And then you just need to pick up like this number. So before I do that, I'll just make a sub function to actually find this, right? When like the largest element. So that would be this. I'll state, however, my epsilon. And I'm gonna give it like a, I don't know, like let's give it a few numbers here, right? So here, this is the smallest we can get, something like that. Okay, so I have my epsilon here, and then I need to make a def find largest how's it called, absolute off diagonal. Yeah, that's a big one. So then we can use like our matrix here, and we're gonna make it dumb right now. So this is only for a 2 by 2, right? So if matrix, the off diagonal will be like 0, 0, 1 is bigger than, I'll need to take the absolute value here. So it's bigger than matrix 1, 0. I'm gonna return matrix 0, 1, and otherwise we just return matrix 1, 0. But this is not true because we need to take the absolute value. Absolute like then. Can I just, yeah, I can just do that. Yeah, okay. Absolute here, and absolute here. Okay, so that should be good. If it doesn't crash, and then I could just, yeah, I'll just run that, and I do find largest absolute off diagonal element, and I'm gonna do stemp. In this case, it should be it's just gonna be return me 4, right? It will just return me that and that. Good. And then if I change the stemp to be I don't know, like 1, 0 equal to 10. Okay, if I do -2, if I do -5, good. I don't want this. I want it to return me a tuple then. I want it to return like 1, 0 here, and then 0, 0 here. 0, 1 here, right? So this is only for 2 by 2, and then what it does is find the largest absolute diagonal element, return its index, because the index are quite important in this specific implementation. So I get 0, 1 here, 1, 0 here. Perfect, cool. So let's not change anything. Let's get that back over here so that we find the right stuff. So I'm able to do that now. I can find the largest element. So by doing this, I can then get myself that. And my only question is how the heck I'm gonna calculate this stuff. It's the arctan of, what the fuck? Wait. By arctan 2 okay, yeah, okay, got it. Yes sir, I think I got it. So okay, I'm gonna have another function, find theta, and I'm gonna give it my I'm gonna give it my matrix. I don't care, right? And then like I'll be able to call this, and this will be my little stuff. So 0.5 times like my off diagonal, my this element, right? 2 times like this this element. So I'm gonna get my I and j from find largest blah here, give the matrix, boom, I get that, and then I do 2 times the matrix I and j here, and the stuff that goes in there is this one. So it's gonna be matrix 0, wait, no, matrix I minus matrix j, right? That's the thing, right? Yeah, okay, cool. So get that, and then this is gonna be my theta, and I'm gonna return that. I think it's gonna work. How do I write theta? This is not right. I think I have h too much here. This is off. Return theta. Is this good? I think so. Okay, wait. Line 3 theta, blah blah blah. There's a missing parenthesis somewhere here, yeah. Okay. Okay, and then I can do find theta of my S temp. Okay. I have no idea if this is I don't know. I get minus 0.78. Maybe it's a good I have no clue. And we're gonna have to iterate on this to figure it out. But now I can find the theta, and this theta will go and then iterate here. Do I need, like because I'm right now what I'm thinking about is when I'm gonna stop, right? Because if I bury the find largest absolute off diagonal thing in there, I'm not gonna be able to recycle that to find if this element is even worthy of going. So I'm gonna take it out actually. I'm gonna give the I, the j. I'm gonna take this thing out here, right? And how it's gonna work is gonna work like this. I'm gonna do it like that. I'm gonna do it like this first, right? And then I'm gonna have a check if smaller than epsilon. Epsilon, right? So if my S temp at I j is smaller than epsilon, right? Like we quit, right? We're done. We're done here. So then I return whatever I do. I'm gonna go and return my S temp, which is gonna be my actually S. Now it's like it's not temp anymore. It's like gonna be S for real. So this is how I'm gonna stop. Like returning here is absolutely useless because I'm inside a cell in a notebook, right? But I'm gonna jam this at some point into a function. So I'm just gonna call it like get the stuff, call the function. Yeah. So this is our stopping criteria over there. And if it's not that, like if like in this case it should be okay, outside function. Okay, so here I'm just gonna do I don't know, print. Right. Stop. Right. Shouldn't do it. But actually it did wait. If how come? Oh, I think it's the absolute. Jacob. Perfect. So if the absolute value is smaller than the epsilon, I get out and I stop. Otherwise, I find the theta, right? And I'm gonna get my theta here. And with that theta, then I can do something. I can do, I have that. I can build this thing here, right? Which will depend in which scenario am I. Yeah. So, like, I'm gonna make another function. And by the way, I like that. Like, one thing I love to do in programming, and like with this kind of lead code type of way, it forces you to do that in some way. Like if you have trouble, you can split the problem, but it's gonna split it like functionally. So you're gonna have like each of this will build you like a function that then you can compose together, right? There was never a case in anything that I program where like a functional type of mindset was not the best thing you could do, right? Like having states everywhere and having like everything mashed up together and complicated, I find it's never good. Like it never leads to a good solution. Usually like you have your ugly problem like this, right? And then you just poke at it. You poke at it and then you figure out that like, hey, at some point I need to find theta, right? And then like in some other form I will need to, I don't know, like find the maximum absolute whatever, right? Okay, I still haven't fixed my problem, but then you keep doing this motion, right? You keep doing it, and at some point the problem kind of solve itself. Like you will see it, like whatever you're doing, even if it's like a research type of project, like everything will start to converge together, and then you're just gonna have more modules that like are getting built faster, and like you're just gonna go through it. And they never worked the first time, so usually like you think this was good, but actually like this was not good. But when you're gonna go back and try to fix it, you just have to focus here, right? Versus trying to debug something that is not working, that is big like this. You don't want to be in this situation, right? So even when I was like making my code for let's say a pipeline that was ingesting a lot of participant data, and then like I wanted to like get all of the pieces together to get to my output, my trained model that then I was able to interpret. Every time what I did was I tried to get like the first block done, right? And then I get another block done that is doing like 10% of what it should be doing. And then I get the last block done. And I try to connect them together. It's not what I'm supposed to do, but I get to like the input raw, right? To like my output that is kind of okay, but it's not the stuff that I need, right? Then I can add more block. I can go there and add the missing block in there. I can change this to have 2 blocks instead, right? I can have this other thing over here. I can do a lot of stuff after that, and then I iterate on that. I always felt that this was the best way to go. And like I always liked, this is a bit of a tangent, to go from like the raw data. I hated when you had to make some modification manually on some stuff, right? It's usually best if you have the raw data in like a big messy pool, and then like you have like all of your kind of processor that is taking the data, right? Every chunk of it one by one, and then is able to process it to get it to like a cleaner form, right? Because then you could technically save all of them here, and then you don't have to run the pipeline like crazy like every time. But I feel like when you start to do like manipulation here outside of a pipeline and you were wrong, like this is where you get very frustrating as a researcher, because then like let's say you normalize all of your data point like this, there's 100 of them, right? And then you did it some way manually with like a graphical user interface. Then when like it actually was a problem in your pipeline down the line, you're gonna have to redo that again, and then which version of the file was good. I hated to do that, so I always keep the raw file somewhere, right? I pull from it, and then I process it until I have a clean file for now that I can play with and make my pipeline with. And if I have to change one of these, I just run the pipeline again, right? Anyway, so a bit of a rant, but like always best in my view to do that. Okay, so where was I? I was trying to make build givens matrix. In this case, it's called a Jacobi, so I was going to call it Jacobi matrix, right? What is it called? Jacobi rotation. Build Jacobi rotation matrix. And what I need to give here is just a theta. I give the theta, and that should be good. And this is purely for 2x2, right? So I get that. I have the theta. And now I know that I need to do cos in the diagonal. So theta, sorry, I'm gonna make like my j equal, and then numpy array of 0, 0, and then I have another one here, right? I think there's a better way of creating this array. But then I'm just gonna populate each of them. So 0, 0 equal, wait. Okay, blah, blah, blah. Yeah, just this is gonna be good. Oh, G, 0, 0. No, of theta. Okay. And then same thing for, I think I can just do this. J1. 1 equal, same. And then is gonna be my, this is where I will need that. I'll need the I and J here also. I, J. Because then, how did this say? The ij get the positive, the ji get the negative. I think that's roughly what it is. So j get mp sin of theta. J I equal np sin of theta minus, right? So here, so theta is our rotation. How did we call this? Our rotation angle. I and j are the indices of the element we need to are targeting. We're returning the Jacobian Jacobi matrix, which is J. Okay, I think that's good. Let's try it out. So build DAC theta I J. Theta is not defined. Wait, fuck. Is it? No, it's good. Should be good. Is it because of here? Theta. Tap tap. Oh, I'm returning absolutely nothing. I'll need to return J. So I get 0, 0. Does it make sense? I get 0, 0. Fine. Okay, this is that. Wait, what? Why is it? Wait. Something is a bit weird here. Okay, let's try that back from the top. Okay, this is good. This is good. Work. It's not returning int. Yeah, it's returning this. Okay, ij. Why is it freaking out? Oh, okay, here, find it. I and j. Good. Why though? Why do I have a 0, 0? Oh, maybe I can't change these. Wait, I'm gonna test it out. NP class theta. Yeah, I think maybe it's this. I can't do that. I think this is not allowed. Is it? What is going on? Okay, no, this is good. Okay, so what's up when I do say 0, 0? I'm most likely doing something stupid right now. So can I? Yeah, I'm most likely doing something stupid, right? Okay, wait. I don't get it. Wait. Class. Right, and then if I go here, why is it not doing anything? Why is it 0? Is it because of this? This is still 0. I'm kinda perplexed here. What the fuck is happening? Okay. Is this just a view? What is going on? Oh, I think this is what's up. I'll need to do this, I guess. Wait, no. Okay. Yeah, this is painful. What the fuck? This is the first one. There's something I'm not seeing here. What is going on? I don't get why I can't see it. So I'm returning J here. And it says still that it's 0, 0. And even here, when I index into it, I still get oh, I think you're right. Because, yeah, okay, right. I think you're absolutely right. Oh, thank you very much. Thank you, Eunice. You saved me approximately, I think, 25 minutes. Okay, let's do it like this now. I think this will be cleaner. That. Yeah, okay. Is it still working? Yes. And I don't want to. Okay, good. Okay, perfect. This is this the right one? What is our IJ here? IJ is 1, 0, so it should be this one. And what we're outputting here with our J. This guy, is it this? This guy get the positive. Okay, cool. Well, we're making some headways. So now I have my J, right? Now I can calculate this big thing over here. Transpose of J times, well, whatever the heck we already have, times that. I think this is how I can make the transformation. Let's see. So I have NP transpose on J, and then we do that. A stamp, and then we do that, J, and we get that, which seems pretty weird, I guess. What was the answer on this? We're not gonna get it first try for sure, but the diagonal was something like this, 3, 3, 1. But this is the first iteration, and we're getting some kind of weird number here. That's a 5, 4, and our J is going to be really small, and the transpose over J will be what we're expecting here, right? So if I do this and that, we're going to get that number, and if I do this whole thing, I feel the numbers are very small. For some reason. Oh, that's still 9. Oh no, it's 9 and 1, and then 2 very small numbers. Right. Okay, so yeah, I misread. This is good. So we do that, and this is gonna be our S stamp still. It's gonna be that, and then we can do this thing again, I guess. So I'll try to make a function now to just make a step into it, right? I could do that. Do I need to compartmentalize? I have to find the theta I can find my largest absolute of diagonal, I can build my Jacobian matrix, and then I can apply the step based on that. But anyway, I will need to take this J and then do something. I'll just do a while loop here. While my epsilon here. Okay, let's do that. So we're gonna do this stuff here, and we're just gonna find the largest epsilon first here with our S temp. This is where we start, right? We're gonna get our S temp, which is gonna be this. So this is good, like that. We have our epsilon that we've defined, and then while the absolute value is this, then we do stuff. So print, do stuff, and then we just break when we're out. So print, we're done. So that's good. And then we do like the steps that we need to do. So the first thing is this one. We're gonna do it the last one of these. So we're gonna do it at last, and it's gonna find my next I, my next J, right? Because we already did it here for the first iteration. So we're gonna do next for the next one, and then with the one I have right now, I can find my theta, right? Find my theta here, and my matrix will be my S temp, and that will be my theta. And then my theta, what I do with it is I'm gonna wait, where did you with it? I find my theta here, and then I just build my Jacobian matrix here, right? There you go. And then with this, I can like update that. At this point, I have my J, right? And now I have my new S temp because it's equal to this. And that should tell me, I'll just gonna print it. Print current smallest value. Well, no, current largest of diagonal value. Get that, and it's gonna be S temp I J. Okay. Of course. Of course, everything crashed. There's red. Absolutely. There's red in cells that I haven't touched. What the fuck is going on, man? What is I don't know, like yo folks from DeepML, if you're watching this, I want to run this cell, but it's not letting me. The variable stemp was defined by another. Okay, I get it. I think it's just a warning here, because I'm doing like something like disgustingly stupid. Actually, I can just take this up and clean it up a bit. Yeah. Everything fired up, right? Oh boy. Okay, this is funny. I didn't want to do that, but I'm just gonna clean up starting here. This one I can how can I delete it? Can I delete this cell? Is there a way? Wait. I can create the output, yes. Can I just, is there garbage in there? Can I cut? Okay, I can cut that. Okay, it seems like I can't necessarily delete any of them. I can clear the output though. This one I don't need anymore. I'm good. Doop, doop, doop. Yep. Okay, this is what we have. I have this function, this is good, this is good. I don't need this one anymore because I already did that, and this is my A. Yeah, good, this is perfect. Okay, cool. So can I just run this without what's up here? Okay, this is dead. Dead. Okay, let's go back. Yes, I'm just gonna put it down. Good. This one I don't need it. If you're hearing like a lot of pumping noise, no, it's not my website. No, it's not. I'm using it a lot. I wish I built it, but it's really not my website. I think I linked to the guy that was making it, the Mo 18. Yeah. But like these features are new. The notebook mode is kind of new, and I kind of like it because there's data science like a exercise in there. So it's nice to have like this flow where you literally have like a notebook that you can play with without having to go to collabs and stuff. I don't know how they did it. I think there's I don't know which library they're using. Okay, wait. This cell raised an exception. Name error. stamp is not defined. Well, it's defined there. Okay, here it's raising this. Okay, no. Yeah, perfect. I don't need that one. So this one also can die. What I was saying, yeah. If you're hearing like a loud noise, is because right now there was a heavy rain in my location, and like most of my terrain is like completely flooded. So my pump is literally like working non-stop just to get water out around the house. So yeah, that's what you're hearing. Okay, so we're done. We're good. What's the answer? Wait, I think I can just do stamp. We're not done. Like this is not this is not it. What the hell is going on? Are we even? No, we're not doing stuff right now. Wait. We're doing this, and then we're doing that stamp. If it's smaller than epsilon, what is like? Are we doing epsilon right now? Well, the absolute value of ij, and what's our ij here? Printing the whole family. 4. How come we're not doing stuff? Well, this is smaller. Oh, sorry. Yeah, it's just fucking dumb right now. Well, this is bigger. Okay, we do stuff. Currently, just how diagonal is this. We're done. We have a 9 over here. We have 1. And I do believe... What did it say here? Wait, where was I? When we get here, we're not getting sigma directly. The squared singular value of a. So I just need to square root that. Yeah. So if I square root them, I should be good. Thanks. Thanks, Eunice. You're literally debugging me as I'm doing it. Okay, so I can just do square root of that stuff. So my sigma is actually going to be, well, actually, wait. My sigma s is going to be equal, actually, this is going to be, is it, yeah, it's going to be s equal np square root of a stamp. And that's what I want. I want that s. Wait, oops. Oh, I think we got it. Wait, what was the answer? It was 3-1. And what we got? Oh, 3-1. I can remove these. I don't care about them. Yeah, 3-1. These ones should be zeroed out, but it doesn't matter because we're just gonna extract these. That's what we're gonna return. So in our case, it's gonna be like s equal s stamp. Sorry, s on 0, 0, and then s on 1, 1. That's gonna output. It's a numpy float, perfect. Actually, there's a better way of doing this. Like that, I guess. What? Wait, no. I'm doing something stupid again. Oh, okay, yeah, I know. Okay, there you go. 3-1. We got it. Ooh. Is it 3? I am on your side. For me, it's still. What time is it right now? It's 10 for me. 10 p.m. So I still got like a few neurons left. But as I'm speaking right now, like I feel more and more sick. So I think I get like 30 minutes left of brain power before I completely crash out. So S is good. So we got S, right? So like if you look back at our stuff, effectively what we've done is just this. We just went like this. We absolutely ignored the U's and the V's, right? We just went straight with the S. And to be honest, like I feel like in most problems, like that's the best way. Like if you go about and you ignore a lot of the stuff, a lot of the requirements, it's the best way to go about like getting to something that is working and then with the least amount of pain possible. And I've caught that with a lot of researchers that were more senior than me and like good developers, right? I have one on my team and he's really good because the first thing he do is that he look at the requirement, he throw them into the garbage except one. And he try to do that as fast as possible. And once he has it, right, then like he already have like a path figured out and they tack another requirement. And then they tack another requirement again, right? So that's kind of how like the best software I've seen or the best analysis actually went is that they go for wrong and done first, right? But like not completely wrong, just like a bit wrong. Just a bit right, right? So you go at it, you do a bit right, and then you can celebrate because you know the rest will be kind of like a piece of cake. I'll be there 2 hours later trying to debug this mess and we can replay that clip. But yeah, so you get one bit like out of the way and then like usually you already found the most painful part, which is the flow. You know like that the flow is good. And if you have the path from A to B, right? But actually it should be A to like Z, then you increment like a letter and stuff. So now we can do U, right? And since we've done this already, we actually can go through this and then every time we just iterate on that guy. So we first just need to make the identity matrix. And I think we can do it with the I guess. Is that it? Yeah, I. Yeah, and I just need to give the size of it. Okay, so this is S step my u will be npi, and we have to have float here, and my v will be npi same, and we're gonna have my float, right? And this I'm gonna disable, and I'm gonna do it right now. So then here I am effectively updating my temporary sigma, and here this is for my next situation, I and j target, and now I have to update my u by accumulating j on it. And to do that, what do they say? I think, wait, who said what? I think here in this case it said we apply the rotation, we construct j, and then update v or u by multiplying it by j. Here, when they say multiplying it, are we saying like a dot product, or we just go through like the whole? Yeah, this one I'm not sure. Is it like element wise or an actual dot product? What did they say over here? Well, this is just for S. You're not gonna tell me for the rest of the stuff. Wait. No. Okay, wait, again, no, I think it's a dot product that I have to do with this. Yeah, I think so. Okay, anyway, let's test it out. So I'm gonna do still u equal g u, I guess. And I think we're gonna be done here. Here's the sigma, print, here is the u. Okay, what do we have for you? We got it first try. Wow. Is that it? 70? This is the u. No, we didn't get it. We actually did not get it. It's a minus. So we have minus 0.70 and another minus here, and this one is like there's 3 minus. Like this thing is absolutely not correct. Why is it like this though? Yeah, it won't change because it has the same. My stuff is reversed completely. I'm not sure. I am truly not sure here. Is there something I'm missing? Is there a manipulation at the end I have to do? Update v or u by multiplying it by j. Wait. So of course we're gonna get that. Why do we have so many minuses here? Minus, and we have that. Maybe because I'm wrong in how I'm building the Jacobian matrix, maybe? Is this one wrong? Do I get still the same answer? I get 1 3 flipped, and the U is garbage still. So this is not changed. So here, this is not the issue. I'm good here. There's no issue about it. I think it's how I'm accumulating these, but I have that like this. I don't see how I can get that if I start with the identity matrix. I don't get it. It's gonna be like this, 1 plus. And this, my J is like that right now. And these are positive. Is it my theta that is? No, my theta should be good. And my epsilon, like, I just do one iteration and it goes down. Oh, yeah, I might be right. Let me know. Okay, I'll continue because I think it's just I think I'll see it with the other one. Actually, I think if I use the other one, I'll be able to see it more clearly because this one is symmetrical, which is cool. But it makes this a bit weird. Let's use this one actually. By the way, folks, for those that don't know, Mo Shabbat in there is the one that built this stuff. So if you have questions, you can ask away. Well, I'm trying my best. Okay, wait. I have to stop that. Okay, here we're actually doing some work. Nice. But then I'm just gonna like mess up my whole. Like, is it still running? Yeah. Oops. Okay. Let's not do that. Let's have a maximum amount of repetition just to avoid max iteration equal, I would say 10 for now, right? Current iteration, we're at 0. And if like this or max iteration, the current iteration is bigger or equal than max iteration. And then here we're going to be able to do current iteration plus equal 1. Wait, what? Okay, wait. I do stuff, and it still doesn't stop. What did I do? Okay, wait. Wow. Okay, no, sorry. Well, this is true, and current iteration is smaller, strictly smaller than max iteration. No, I'm still a bit dumb, sorry. You can see the last print cells absolutely dissolving right now. Okay, wait, absolute value is bigger than the epsilon, and the current iteration is smaller than the max iteration. Yeah, and it's smaller than that, yes. And my current iteration to the current iteration plus 1, so should be good here. Hey, this one needs to stop. Can I stop it? I don't think I can. I guess it will eventually stop when I'll mess up the whole thing. I can't reset it. Yeah. Okay, let's save this. let's refresh and see if hopefully I didn't lose everything. Oh yeah, oops. This notebook is temporary and you will receive normal code editor will be preserved. Ah shit. Did I submit that? No. Okay. So we lost absolutely everything. We absolutely lost everything. I think I should not have. Yeah, I think this was a mistake from my part. Like let's actually just run it again. Find. You were done, guys. Yeah, we're gonna be there for a while. Maybe I could rewind. Yeah, I could maybe do that. I could maybe rewind the live just to the part where I can still see it. But I think I'll be alright. Like I think I got it off the top of my head. So diagonal, we have this. Let's just do this. We're gonna have this one. We'll need a matrix here. It's gonna be 2 by 2 for sure. So if matrix 0 1 is bigger than matrix 1 0 or I can I ask, like, Mo, can you get it back from whatever you saved in your server? Okay. I can give like 0 1 here, or return 1 0 over there. So this one is good. I remember this one. Which one was hard? Is it find theta? Because find theta, I don't think it was that hard. I have my matrix, I have my I, my J, and then I do like this stuff, right? I just do that. It's literally just like no. Yeah, I don't need any of that. I just need that. Right? I think this is it, right? So this one, I have my IJ. Okay. So np.arc10.2, and then it's like theta equal 0.5 times that. And what we do is we are doing, no, I need the matrix. Yeah, for sure. Okay, yeah. Well, I think we're converging. I'm gonna go matrix I J 2 times, right? 2 times that, and then we do matrix I minus matrix J. That's it, right? Yeah, that's it. So 0.5, and I return that. Return theta. Okay, guys, I'm speed running this. Like, this is easy. And build the Jacobi rotation matrix. This one was a bit harder. Yeah, this one was. I have my theta in there. And how did I do that stuff? Oh no, it was not too bad. It was actually not too bad. I create my G equal my numpy array, and then I can do this, and because I'm not stupid, I'm gonna be doing this like that now, and this like that. Well, like this. Well, no, wait, like that. Duck. We're getting there, and then I do D type. Go float, right? And I go G 0 equal G 1 equal np dot cos of my theta over here. Why do I need I and J here? Oh yeah, right. J is where I'm gonna have sin positive, and I is where I'm gonna have the sin that is gonna be negative. And Okay. Before I'm gonna press go, I'll just double check if it's like all good. Yeah. Um, okay, cool. Perfect. Yeah. Do work on it. And I guess, like, guys, you were already saying it that if you hit refresh, like, this is what will happen. So I don't feel too bad about it. It's 100% my fault here. So let's do it with a bit more brain cells now, right? We're gonna take that, jam it here, remove everything, right? Here, print done safely, right? I'm gonna go like this, a current iteration, and then I'm gonna do nothing. I'm gonna do stuff, and I am actually yeah, I'm actually I'm gonna copy paste this in another window. Just give me 3 seconds here, right? I'll just get that, and can I have a text editor over here? Okay, here. Yeah, don't steal my super base password for the tutorial I was doing. So that's that, and then here. Okay. We're good. Okay, let's actually try it out with our little brain cell. So if this is smaller than max iteration, we do stuff and we just iterate. Should be chill. Like I should not have any issue here. I'm just gonna put it here. Okay, spray. Current iteration. Ah, you see. I was being an idiot. Right, that's bad. Okay, cool. Reduce. Okay, guys, we got it. That's good. This is good. And so that like this I can delete. This is good. Okay. Let's run everything one by one. I think I still need my A. No. Yeah. Do I need that? No yet. I'm just gonna put it up from. What was it? It was 1, 2, 3, 4, right? 1, 2, 3, 4. Okay. So 1, 2. 1, 2, 3, 4. Good. That's good. Hopefully this works. And I can theoretically go. And it literally didn't work. Good. I'm on a free plan, so you can't install much here. And I was doing a tutorial on Scrimba, which I greatly recommend. There are good folks over there. Okay, wait. Epsilon is not defined. Aha. So I just need to define it over here. Epsilon 1. Okay. Yes. We didn't crash anything. We're getting there. I don't know if it's working though. This is my. I have to just clean up a bit my. Okay, I know I do stuff. Over here, I'm just gonna say the iteration, right? So iteration. Current iteration. Okay, that's that. Current largest off diagonal value, that's still valuable. I don't need to print J for now. I think that's good. So this is kind of oscillating. but it's not going down that much. And then my sigma is this. What is the sigma that we're supposed to get? Supposed to get 5.46, 0.36. No, we're far. We're not there. Do I need more iteration than that? Let's go with like 20 or 30. Let's go with 30. I think it's getting there for this one, not the other one. The other one is not getting there that much. But the largest off diagonal is still big. The U is looking like that. It was supposed, oh, well. It's kind of inverse, no? Yeah, like it's not the right, like these ones seems to be flipped with what they should be here. Maybe it's still good, I'm not sure, but like that definitely is not not good. Let's go again for like, I don't know, 60. Are we converging yet? Now we have 2 and then we have 4. 2. No, we're not getting close. And my largest value is still like that. The U's are not getting there too. So, yeah, it's nice. Like I like Scrimba because of the fact that you can always pause the tutorial and you create a branch in like the tutorial, and then you can start to kind of mess around and test with the code. I find that just the idea of it like pretty cool. But like right now it's not working. So what the heck is happening? So we're exiting, we're doing this. We're doing the square root of all that. Maybe I didn't write the Jacobian properly. Is this it? 0 NP cos theta. And this is float. Is this accurate? 2 times matrix, wait. Oh wait, I'll try it out with 1 2 2 1. That will tell me if like I'm just not doing it well here, and I'm gonna do it for like 10. I get 3 1 on the first one, and this is a bit weird. So I think it's, well, either it's requiring a lot more iteration for this very small matrix, or I'm not really good at it at the moment. Oh, I think it's converging. .46 and 0.36. 5 rough and 2.12. So I think it will need a bit more time. These are negative. Yeah. Let's try 200 maybe. And I'm not gonna print this every time. I'm just gonna print it like if print iteration modulus, I don't know, like modulus 10 equal 0. I'm gonna print that. Okay. So should, yeah, and I want to print like, okay, yeah, I'll print this down. Okay. Okay, cool. So I'll can increase this by like 200, let's say. I got the feeling that we're not getting close. Okay, wait. Let's go for 600, but then we're gonna fix the code. It's getting there. You see what I mean? Like the sigma is good. It just flipped. right? It's kind of flipped here. And the U, no, the U is messed up. The U is not doing great at all. I'll give it. I'll give it 1,000 iterations right now. And if we're still not converging at 2,000, I think it's fair to say that like there's something messed up. So we have 3.046 and 4.55 on the sigma. The U is not doing great either. So let's actually fix the code, because I don't think this is the issue. I think like we just messed up something. Yeah, we just messed up something. So let's see, find largest absolute off diagonal. So we have matrix 0, 1. If it's 0, 1 is bigger than matrix 1, 0, we return 0, 1. Otherwise, we return 1, 0. This one, I think it's a check mark. I think we're good here. I don't think there's anything like I don't think there's anything crazy here, right? So find theta. Maybe this is where we messed up. What is going on here? So we are doing ij. This is good. This is good. Is it the 2 that we're messing up here? Wait. We're doing arctan 2, and then we have 2 times ij, right? Is this what we're doing? 2 times ij. Yeah. And we're using arctan 2, and then we have our nice 0.5 here. 2, and then we have ii minus jj. That also should be good, right? And then we return that theta. Are we using it properly here? We have our S stamp, which is a, oh wait, is this good? A transpose, ooh. No, that's not good. Wait, which one was it? Wait. I think that's that, yeah. So you see, it's A transpose times A, but I'm doing A. Okay. So this one is messed up. We need to be like that for my U. I think that will explain some things, but I don't think it will explain everything. So if I do 1, 2, 1, 2, 2, 1, I should get the right answer, 3, 1, and then like, is this is the format? Yeah, I messed it up so much I can't see. Okay, nice. The U is correct. So one mystery down. Okay, so for those that haven't caught that, including me, the issue, it was this part. You see here, for the U calculation, like we need to have A transpose dot A, not the other way one. If we want to have the V, then we need you do the opposite, the thing that I was doing. So this is the spot. Okay, so if I do this iteration, I get, wait, I'm gonna do this and do this iteration. I'm getting this down. Okay, and then I could do, let's say 1,000 iteration. What we're gonna get? And I think it's still not getting closer, right? I think even with 2,000, at this point for such a small matrix, I feel like this is for sure not the way to go. For the other one, yeah, this is for sure not the way to go. Perfect. So there's something messed up somewhere else still. Okay, so this one we double check. The building the Jacobi, maybe we're missing something. We're doing cost of theta here, and then this one we're doing sin ij ji. And return j. I feel like this is okay. I don't think like this is like some wild shit we're doing. But is this that? Is it because we're doing it this way? Because it depends. In this, it's written like that. In the other one, it's flipped. I don't think it will change anything if I change them. I don't think it will change something. Could try. It should not do. Wait, what? Is this the answer? No. Okay, wait, which one I have right now? I have 1, 2, 3, 4, right? And then it's going for just like one iteration, I guess. I'm getting 0.36, yes, and 5.46. Okay, that part is good. But then I'm getting 57, 81, minus 81. Yeah, this one is messed up. Like I feel like the U I'm not getting properly. Right? This one I think I'm not getting properly because we have 0.81 here, 0.81 on the diagonal, and then like these ones are kind of flipped up. But in this case, it's like this diagonal that is like that. Like the 0.57 are diagonal, and these ones are also flipped. Oh wait, no, I'm not looking at the right stuff. It's this one. But I'm getting this. Huh. Okay, so with my little change in here, is this still working or not? Oh, this is flipped now. But it's the right answer for it's the right answer for this one. No, it's not. It's yes, it is. Okay. For the U, it's the right stuff. For the stamp, it is not. It is flipped up. I guess it doesn't kind of doesn't matter that much, but like it just, I think I'm mixing up some stuff in terms of like the orientation. Because now I'm doing G, let's transpose that. Is it these ones that are flipped up? Aye. Okay, wait. I think this solved it. Yeah, this one is good. But not. Yeah, the U is good. I think it changed nothing. But I'm doing this here. Or like that. No, it didn't change anything. So that one was already good. It makes this not work. Okay. 1, 2, 3, 4. So like these ones are flipped, and the diagonal seems to be completely flipped also. But this, I think it will change something here though. No, it will not. It will not change it. Absolutely. Why am I getting this? I'm getting the V now. have at dot a. ATA. Oh, ATA is for, yeah, you have to change the way it's written because it's a bit confusing for me, right? So so A transpose A is for V. So I'm getting the V here. Right now I'm getting the V, which is that. And that's kind of okay, but flipped. So that's the V. And what I'm trying to get is at the moment the U. So it's that was good. So I was trying to get this. I was trying to get A NP transpose A, right? So I'm trying to get to follow that path to get that. Yes. And right now I'm getting it like this. Yeah, that's that. So do I need to? Then I can actually follow the formula that makes sense. So this one, this, like that, this, like that. But then in this case, it doesn't stop. Yeah, that formula is not good. It's I think it's the other way around. Okay. J. Okay. It is flipped. The indexes are flipped. I'm getting this one, the U now. The U's are completely flipped up. My 0 and my doesn't matter, I guess. Is the stuff at the right spot? For the U, so, wait. For the V, I think it needs to be VT because it's a V transpose, no? Well, I'm not sure what I'm returning. Maybe the turn matrix. There's a transposition here. Okay, maybe I'm just, yeah, maybe I'm just fucking dumb. I think that's the what? Wait. No, how did I do it? My identity seems to be okay, right? I don't think that's the issue. You know what? Let's move on to the V, because I think if I do the V properly, that will help in some way in figuring out what the heck is happening. I'll call this stemp U. That need to look like, oh wait, geez, wait a second. I'm not gonna change the whole thing. I don't want to do that, because if I do that, no, I think it'll need to be two separate track. Because if I do it right now with, I'll need to get this whole thing into a function, and then just run it twice. Yeah, I'll need to run it twice. I don't want to deal with like we're trying to insert the two together. So the def get I don't know, solve sigma. I give it my matrix, an epsilon, I guess. I'll name it what? I'll name it's usually A. Yeah, it's usually A, so I'm gonna name it A. I give it my epsilon in I can give it like my max iteration. What else do I have to give it? Yeah, that's it. I just give it that. So then I set my current iteration to be equal to 0, and then depending, I'll do this transformation before, and then I can just do my accumulator matrix, right? Which is gonna be this. Right? So this is U or V, depending. And then I do the rest, which is exactly the same. I'll just do the whole thing like this, boom, like that, over here with annotation. And I just need to replace that by that. So we're looking at A here, this is A still. I have this, I have my current iteration. I'm gonna have A again. A, I'm gonna put it there. A changed now. This is still A. I don't care about that too much now. And then I return what? I'm gonna return A, which at this point, like sigma equal A, right? So I'll just name it sigma now so that I'm not confused, and I'll return it my accumulation matrix. And that thing I'll need to change here and here. And I think I'm not messing up anything more if I do it like this. I think so. Okay. So now I can just call it solve sigma, and I'm gonna solve it for this one. So if I do this as temp, I'm gonna give it that. I'm gonna say it's gonna be 100. My epsilon will be the same, and then I'm gonna have that. Yeah. Oh, I think I'm missing a step. Yeah, there's these steps. So I'll do it like that. Here we go. A is in there. Boom. We give a small s now. I'll call them sigma. I hate small letter name. Sigma. This is gonna be like sigma V. This is sigma M, and no big letter here. This is actually just say it. Sigma vector. Oof. That's the matrix here. Here again. Okay. Oh, why am I missing something? Okay, so run that. Of course. Yeah, I can call it I think it doesn't matter. Sigma 10. Okay, what do we get? We get 0, current largest. What do I get something out? Sigma vector and my U in this case, right? And I'm gonna print a sigma vector. Well, actually, I think we should do that. And my U. the variable u was defined by, I know that one. How come can't I just like live with this problem? I'll do it lowercase u, I guess. U matrix. Okay, guys, we're converging. We're about to get there. So this is for the u, right? And I can run it, and it should not crash when I run it many times. So that's good. Now, theoretically, I can just do that and flip these like that. And this is gonna be my v. I should get the same stuff. Wait, what? Wait, no. Wait, let's call it temp u. Right, that should be good. Okay, this one, let's call it v. Wait, no, this one is u. Okay. Okay, this one is not gonna freak out. This one, put a nice v in there, put the v there, and then this one is a vector v. And then we get that, we put it here. I like that this version of a Jupyter Notebook, Maremo, is like very aware of the issue of different cells kind of overriding each other. I don't know if like forcing you to stop is the best way to go here, because like when I do a notebook, usually I have a crappy notebook, right? I go through it like crappily, and then I kind of refactor it and I put it into either a better notebook or like a Python script. Yeah, but anyway, like it's not breaking anything. It's just like yeah, I think it's fine. Don't listen to me. So okay, now if I do it like this, I get the same sigma. I get a different v and u. Which is wrong. It's not the right one. But I think it's getting closer, right? It's getting closer. I got I got the right numbers, folks. It's absolutely just flipped. So there's something in there somewhere I'm not doing properly. I think it's maybe, it's either one of those. It has to be one of those. How I'm like accumulating them together. What is going on? Maybe if I like, maybe in this one, 8 of this is fine. Compute the angle for the Jacobi 0.5 arctangent 2 times this, but in this case it's doing it like this. Okay, wait, maybe it's that, I don't know. Then given angle, construct a corresponding 2x2 rotation matrix. So cos minus sin cos. Wait, why is it doing this? So minus sin. Okay. And then this one is what? So it's doing GT, AT, and G. Okay. Okay, this is good. Yo, this feature is absolutely nice. Like this is good stuff. I like that. Um, this I know what to do. Use given matrix to V obtained by a Jacobian rotation. Matrix using calculated A. Wait, what? Each column after computation, each column vector review is obtained by using each element of. Okay, yeah, I don't have to calculate. This is what I meant. Like, I knew there was some way of like going from one to another. I was just being super dumb. Okay, wait. So I think one part is this. GT, AT is this one. This one I was not doing properly. I was doing it right the first time, but like, so it's GT here times A times G, right? So that should be good. That's how I'm calculating it now. But it is not. Man, I think I'm gonna convert. So there was this first problem, and I think I saw another one that I was doing not properly. Is it that? I'm not sure. Wait. So G diagonals AT by root coordinate system resulting their matrix as eigenvalue AT on its diagonal. But I'm not getting that. I'm absolutely not getting that first shot. Okay, wait. A5445. Different previous step. And I'll put this, and that. I'm actually gonna just print quick my A. Okay, wait. Well, let's go for the easy one. 1, 2, 2, 1. And we have that now. Okay. So 5, 4. This one is fine. Like it has no problem. And this one, we get the same V. I think we get the exact same solution. Deck. Good. Okay, these two are flipped. But this is good enough. Is there a reason why it's flipped? Okay, well, it should be flipped irrespective with each other's. Right, like that. But in my case, it is not flipped like that. But I guess I could always just change how I'm calculating my U. So this is not the issue. This I'm not calculating it like this part. So that might be it. But I know the theta is good when I get it. Oh wait, on the first one, we might be messing up with this. I think maybe this is where we're messing up. Was this it? Okay, now it's flipped. Wait. No, wait. The U is correct. And the V is correct, not the U. I get the same for both. Even though my A is different. Wait. AT or A times. For you. This is for you. This is for V. Okay. Wait, okay, cool. Maybe it's this part. I think I saw something over there. So we actually do this, this, this. Oh wait, do I have to do this every time? I don't think so. Do I? Because that would be just one step. I don't think I need to do this every time. Because this is just for one, like in this case, it's not iterative, there's just one step. I'm not sure anymore. Okay, wait. So this is for my, okay, my U, I get, it's not right, like this is one is flipped, but I mean, it's not that much of a problem. It's either this, oh jeez, we're missing an absolute. I don't think that will solve anything, but like we have that we have that issue, so that already is this. Then there's this one. I'm not doing it like they are doing it here. You see that? Wait, arc10 numpy. Okay, doop. I can just like calculate arc10 like that, and that could solve a bit the issue. I don't think it is. Actually, I think that will does a lot. I don't think it will do anything. It will be arc10 2 times this matrix minus both of these over here, right, JJ? And we do 0.5 times that. That's equal to my theta. I don't think they will have much an impact. Okay. It fucking flipped it. So that's that. And does it do? Yeah, my V stays the same. Okay. Well, that's not the issue. On that front, it's not. Okay. But I get my tree 1 now. So this is that. I get that going. It's this part that is a bit weird. How do I define which one goes where? I think this is maybe where I don't have the best comprehension. Hi Sharon. We're 3 hours in. It's kind of lead code, but like for like linear algebra and like deep learning, machine learning type of stuff. I already put a link over there. It's in the description. Go check it out. It's pretty useful. But right now I'm struggling, so you can watch me struggle for a while. Wait. Which one I was trying to look at? Oh wait, yeah. How do we make the Jacobian matrix, right? So cos minus sin cos. but it's not supposed to always be like that. Yeah, and like I think I'm just messing it up based on it's not this one, the given rotation, because here it says for fixed I bigger than j, the non-zero element of given matrix are given by I bigger than j. Like is it I that need to be bigger than j? Because here it says the j I, but j at the row. Right? Is it the one that is supposed to be minus s? SS is sin. Or is this supposed to stay like that? Oh, maybe I'm just fucking dumb. Maybe maybe I misunderstood. And a 0, 1 is supposed to be the negative one, and 1, 0 is supposed to be the positive one. Yeah, this part I'm not entirely sure, to be 100% honest. So wait, this one is good, and this one hasn't changed. I don't think it I don't think it did much here for the V, but I think the V you can calculate it in a different way. But we get that it's roughly the right numbers, right? So if I test it with the other one now, 3, 4, is it gonna go crazy like last time? I mean, I'm printing like crazy, so of course it will. Okay, what do we have? Okay, these are, folks, we're making progress, right? We're getting there now. I promise you, we're getting there. So these are good, and I think these are not that messed up. Yeah, they're not that messed up. It's just they're not that messed up, so that's not too bad. And the V, we're double checking, this is good, but then we have 0.57 minus, this minus is flip, but it's not too bad. And this one is good. Okay, I can almost live with that. There's just something here that we're doing that is a bit weird, and I'm not sure 100% what. So is it maybe that? Yeah, I'm not 100% sure what's up. Why is it acting like this? Is 0, 1, 1, 0, sin? What? Fuck? Yeah. Okay, I'm not gonna read some Fortran at like 11 in the night. My diagonal is fine. It's just like it's all messed up in terms of like what's supposed to go where. I'm getting the right. Am I getting it right? No, now it's flipped. Wait, the fuck? Did I just change something? Jesus. No, like I take back what I just said. But I'm so close. I 100% know like it's gonna be some dumb thing that I'm just not like doing properly in terms of like where a sign is or something like that. I know this should be yeah, this one I'm not sure, man. Like there seems to be a little thing in there that is not like hitting the spot. Um, yeah, I'll go back to this 2-1 because the example is in that. And make sure to run everything. So 3-1 is nice, and then we get that. And then when I do this, I still get 3-1 properly, right? The U and V are absolutely the same. I don't know why, because I'm just doing that. And am I changing it by, is it like a global thing, variable thing? Do I have an A at the top? Okay, that's good. Well, can I print it maybe? Okay, that's good. Safe. We're good. So print sigma temp u, just to be double sure that we're not doing some dumb thing in there. So this is my 554, and this should give me the exact same thing. Yeah. So we run these two, for sure we're gonna get the same thing. How in the heck did we get two different things here then? Yeah, I am confused. I think the one thing I'm missing is that in here we should supposed to be doing the transformation again, maybe. Is this? No, I don't think so. It's that. That would be too dumb. NP transpose A. That will, I think, will mess up the whole thing. Yeah, I'm getting 9 here. Because, we're doing this, and then I'm taking the square root of A. But now it's so much bigger, so it makes no sense. And yeah, that's dumb. And this is still not it. So that's for sure not it. So this just showed the first step. So that's that. But then if it's the same thing that we're sending in both, how can I get a different V? I can't get a different V. I think the V is also defined as something else in there. We can define it here as, well, U can be calculated as V, wait, I can just do A dot V transpose dot the inverse of the singular value. After the computation, each column vector of U is obtained by dividing each element of AV transpose. Two, 1, 1, 2. Wait, what? How is this the U then? Because that's not what we're showing here. We're showing that output. This is the third matrix. Select the output now. well, at least for now, I'm just gonna transport a bunch of these stuff into my sorry, into like the actual code version of this, so I don't like absolutely nuke my improvements. So give me 2 seconds while I do a quick migration. So I'll need that there. This go there, and this little function will go over here. And this nice fine theta go over here. And this build Jacobi matrix goes over here. I want to get that done. I want to get it like solved and not have to touch it ever again. So that's that. Then I have my U and my V, which is not, it's not that well, not that useful to do it for the two of them. Okay, and I have my V over here. We're gonna start the process of doing our nice little migration. So what do we have? We're gonna have our epsilon over here. Then we're gonna define. I'm gonna jam this nice function right at the top. Boom. Good. Wait, what? Yeah, good. And then I have this one. So we're just gonna move out of the notebook world, because some stuff sometimes happen in notebook world, right? Some stuff doesn't make sense. So that might be the reason that my stuff is not working. I don't have much hope, but I think this may be that. If I was like super wrong, folks, I would have said like, yeah, I have to like double check the maths and stuff, but I'm not that wrong. That's the issue. I'm like very close. What is it? Okay, yeah, this is that, and then we can print it here. Yeah, if I was super wrong, that would be easy one to solve. But I'm not that wrong. Okay, what's up? Yeah, I'm not even. What the heck is happening? Sigma temp U is not defined. Do you mean sigma temp U? Where? Oh yeah, I haven't even. Yeah, that was kind of simplistic. And B A sigma. I don't know. NP transpose of A, and that give us our sigma vec temp U. Yes, sir. And we can run that. SVD is not, oh, perfect. Cool. We're getting there. So basically what I have to return now is my sigma vector U. Oh, sorry. My U matrix. I'm going to refactor that after that. Sigma vector U, and my V matrix, which is going to be wrong. Yeah, I'll have to like I'll have to chill out a bit here. With these, with that, done. Yeah, I can kill this off too. Do we have other stuff that is loading my thing? Okay. So how far am I right now, right? Okay, the first one is good. Like I got my U, and then I get my this one, and I did I get no, I didn't get the second one. They are kind of flipped. 078. Yeah, like these two are flipped. Okay, this is for this one. Because this one is exactly the other one. Okay, yeah, fair enough. And then this one, what do I have? I have these two flipped. I have a first row flipped also. These two are flipped also. That's good. And like, you know, this one is not good. Like this one, there's minus that is at the wrong spot. Okay, maybe just like, yeah, I could calculate the U, the one that I have left, which is the VT. The U I got right. The VT is like, is not right. I don't wanna, I don't wanna do that. Yeah, I could do it like this, but then yeah, I could do it like this, but like it's the U that I got right. It's not the V. I'll just make my stuff much worse. Oh boy. Okay, we're gonna double check everything again. So this one, I think we're good. I think there's nothing. I think there's nothing crazy here. We check the absolute values, 0, 1, 1, 0, and then if this one is bigger, we're gonna return 0, 1, 1, 0, and it's off diagonal, so that should be fine, right? Then there's this whole business of arctan, which we modify, but I don't think it changed anything. Then this whole thing here, I don't like that it's hard coded though. Like that's not. I don't know if it need to be always like this. So this one is always like that, I guess. I'm not sure. So 0, 1 need to be negative, I guess. Where, yeah. Okay. Yeah, are you still there, Mo? Gotta help me out, man. Like, is this good enough, or like we're off the track? I feel that there's something weird in how I'm. Yeah, there's just I feel that there's something weird. But by the way, for those that are new, like just came in, there's actually the guy that did this this puzzle that is in there. So I think you solve for U or V, you could solve for the others. Yes, what? Yes, yes. Is it good or because U I got right, so that's fine. This one I got good, but when you flip it, like these are flip, and if we're doing singular value decomposition, it makes no fucking sense that my first singular value is the smallest. It's always the opposite. Like it always has to be like the biggest one first. And but like yeah, to like when I don't have a symmetrical matrix, it's like everything is going out of the drain. This, you do you think I should? But like when you say that, you say like I'm not gonna get my flames. Oh man, I don't want to do it. Ah, jeez. I think I'm close. Okay, give me 5 minutes. I like just give me 5, right? I'll just think with the 2 brain cells that I have left, and after that I'll check the solution. Okay, right. So I cannot be like having more iteration. I don't think it will solve anything here. We still have. Okay, transpose. That's what we said to do here. At if you got it wrong. Oh man. Is there a wait? You know what? Like, we're gonna first double check. We're gonna double check this stuff real quick. So I want a 2x2, right? And I want like 1, 2, 2, 1. I guess is that? What do I have? No, I have 2, 1. 2, 1, 1, 2. Okay, yeah. So wait, 2, 1, 1, 2. Okay, blah blah blah. Eigenvalue, eigenvector. So 3, 1, and then what do I have left? So my U is this. I got it. No, Mo. I got it right. What the heck is? Come on, man. I got it right. Like that was right. You see here, like, yeah, 0.70 minus this, and it's the same both sides for the V, right? So this one I got, and I'm not crazy. This is good. This one is the same thing. So this is good. And I think you did the same thing, right? No, here. Yeah, I think you flipped it. Yeah. Okay. So I did 1, 2, 3, 4. 1, 2, 3, 4. Okay, what do I have here? Oof. This is disgusting, man. What the fuck is that? Oh, you see, I still got it right. I still did I use the Jacobian method here? I don't know. I don't know what this. I don't know which one what this stuff is doing. But like, wait, the 0.36 is first. 5.46 is after that. Well, this one is absolutely no. Wait, yeah, 0.86. Like this, I got right, and then here I got minus 0.91. 0.40, 40, 91. So this is for the U. What is it? Is it the U? Yeah. So 0.91. No, this one I didn't get it right. Absolutely not. So this one is messed up. The U is messed up here for me. And the V, we get 0.81. Wait, what? 57. Minus and then 0.817. So that's good. I got the V, but the U still didn't get it. This one I didn't get the U. But you didn't get it either. This is too late for this shit. I think you're closer. No, you're not even closer. Yeah, like there's 3 different answer in this thing. Like there's one of you, there's one of mine, and then there's theirs. So maybe they're maybe they're also wrong, I guess. Oh boy. But like I think I got the shape right here. This one like not good. Because of the minus. The minus in my cases is right here. Like that doesn't make any sense. Is it because of this? I feel this might be like almost hallucination at this point. I feel like this is how it should kind of be, but no, absolutely not. Like this is not it at all. Okay, so I take it back. So that's fine. But I don't know what it is. I don't know what's yeah, I'm not sure which part is making my stuff like not get the right I don't know, man. I don't know. Yeah. So folks, I think we'll have to check Mo solution now, right? I know it's a big disappointment for everybody. I'm not gonna get my flames. I don't even know what the flames are doing, but I'm not gonna get it. So we actually have to check the solution. So maybe if we double check yours and mine, we're gonna kind of see that what is what. So you're doing transpose AT. Is it what I'm doing here? No. You're doing V first, right? So you're doing that part here, and then you're using I. I'm using I also. Like we're both using I in there, here, and then if 0 rotation for a 2x2. So if 0 0 is equal to 2 with 1, why are you doing this? If both of them are equal, is it something I forgot to read? Oh wait, what? Oh wait. And why is that? Because they will divide by 0. Am I dumb? Because I never did that. Okay, wait. I'm just gonna incorporate this. I'm gonna steal that. Brilliant idea. So 0 is equal to matrix 1 1. We're gonna say that we're gonna return and then pi divided by 4. Okay. So we're gonna write it like this. Is it changing anything? I don't think so. Right, and I think it will mess up a bunch of stuff. Oof. Ooh, what's up? What is going on? Wait. What's up with piston? Invalid value and content in square root sigma matrix. Okay, yeah. And I still don't have the stuff at the right spot for my U, right? Because they're saying that the U, yeah. Okay, so we're gonna continue our adventure here in the answer, and then you're doing 0.5 arctan 2 times this. I've changed it. Maybe I should use that instead. I don't think there's gonna be any difference whatsoever, but I'm just gonna make sure here, there. Okay, so that, take it here, there. Wait a second. Why are you hard coding it like this? You maybe went to sleep. But like, why? JJ, yeah, because we're always. And that might be my issue. Because I haven't done that. I was using II and JJ. So my stuff is getting closer to yours in some sense. 0.370, yeah. Okay. But why? Okay, wait. I'll read the whole thing. So this you're doing differently, and then you create the rotation matrix like this, and I create it like that. 0, 0 is, these ones are cos theta, this one is theta, and then this one is sin theta, right? And then you apply the rotation, NP transpose. Where are you doing this? Where I'm doing this? So transpose of the rotation R, and then times whatever the heck I'm at right now. It's A times is J again, yeah. And then you're gonna update update A2, yeah. Whoa, yeah. And yeah, I accumulate VR like this. Yeah, I'm doing this too. And sigma is the diagonal element squared. You're doing it in one step. I did the whole iterative garbage. And you find U like this. Because you found V. And you're doing the square root of that stuff. I'm doing the square root of my A, which maybe I should keep because I'll need it to get my V. And then you're taking the inverse, 1s, and then you return, well, you return the transpose here. You haven't said it. You haven't said that we should return the transpose. Okay, that's one thing, right? Because like I'm not returning that. I'm returning it as it is. I think you'll have absolutely no change in like the output. Oh, I got one right. I got one right. Ah, jeez. Okay. And then this one is not right for sure. It's not right at all. This is good. This is alright. This is good too, right? My U is messed up now. Yeah, my U is messed up. Here. Why do? My U is just a bit messed up. I get, and what do I get? Like a invalid value encountered in square root sigma matrix. I don't get it. Well, this is, I don't know. Why is it doing this when I do that? Why is it doing this in the square root? Okay. Because now, like, the only thing I have left is to suck it up. And what's up here? I do should I zero them out? Like, like, I have a very small number, I guess. Is it negative? No, it's not negative. Yeah, I don't know why they're freaking out here. Well, then you wait. This one is negative. Yeah. Okay, I understand. One of them is negative, but it's negative a small number. So I'll. It doesn't matter. Like this part literally absolutely doesn't matter. I could just do that and get the square root of this one, and we should be good here. This is good. Okay, well this one's gone, and I think it will solve my little problem. Let's see. Jeez, come on. Why? Sigma vector and p square a0 a1. Why am I having that now? Oh, jeez. Okay, sorry. Whew. Okay, wait. Okay, we're getting there. I just have my u left here. This is looking fine. This is good. I just had to suck it up and actually calculate my u like a normal person. So here, I don't need to do that then, right? It doesn't matter. I can just get my sigma from here, and we're gonna call it sigma, and this is gonna be sigma, right? And then this is gonna be just v, and this is gonna be my vt, and then I can just calculate the u by doing a at the inverse. How do I do inverse? Inverse. I have like less than a brain cell left right now. Oh, there should be a better way of doing this. I put that here. So we're doing what? So inverse of sigma, and then we're doing this time VT, I guess. Is that it? How did you do it? Wait, no. A, right, that's it. So it's A, and then it's just V. And it's S inverse. Should that should give me my U. And then piling oh shit, Jesus. Yeah, okay. Wait. I just need to diagonalize it. Wait, is that it?
I think it's this. I think it's MP that tag of sigma. I could just return the whole thing. We'll construct it manually, I guess. Oh, we got it. Folks, we're done. This is it. We got the thing, right? We got it properly. Everything matched. It was easy. I got it from the start. I didn't tell you, but I already knew how to do the whole. No, sorry. I absolutely did knew. I still think I kind of got it. I think like the thought process was not dumb. Well, not that dumb. I think we like. I think like this flow of calculating like the U and the V from the identity should have worked, right? I don't still understand why it didn't fucking work. That part, okay, I get like I was able to do this manipulation. I think like this part, the arctan thing, we did properly. I think I did it more complicated than it should have been, right? I think like there's no need for a 2x2, there was no need for iteration. Like we could have just one shot did it because there's only one kind of Jacobian like a rotation. You should be good. Yeah, I think like that's that. So, but still, I think like I think we there's many ways of getting to the end output. Like you get the V first, then you can get the U by doing like the little transformation. I'm still not convinced because my answer was closer to this one. I have no idea. I just Googled the first one I seen. And I don't think they're using the Jacobi at all. There's maybe multiple, like maybe multiple answer. I have no clue. Right? But we're done. I won't have my little flame, but like that's good for this one. So folks, so if you're interested, you can check check the website out. I don't even have it solved. I don't have my solved tag here. But you can double check the website out here. This is a pretty good thing. Thank you, Mo, for having made that stuff. I have a lot of fun in trying to debug these ones. I might do other ones next week or later this week. I'll see. But like that type of stuff, very good to get you thinking and manipulating the stuff, like the matrices and like trying to understand the rotation. And you've seen like to the depth I went in here, right? When you just do it, I don't know, like by hand or stuff like that, or you just read about it in a book, it doesn't have the same impact in you kind of understanding what's going on, right? At the end, you could see that I struggled a bit, but still, like I got a better intuition about how this thing is working and how every pieces are moving. So that's it. I'm gonna go to bed. I hope that this was useful, right? Don't hesitate to ping me if you have question about anything deep learning, machine learning related. We're gonna do other of these type of study session in next week or later in the weekend. And I wish you all a fantastic evening, night, morning if you're in the morning right now. So see you everyone.